So welcome to everybody for this lecture. So it's a great pleasure for me to introduce today Rachid Guerraoui. So Rachid Guerraoui is a leading researcher in distributed computing. He has many influential work in this area, from foundational aspects to practical and application aspects. And he's very known about his achievements, and especially on his work on asynchronous distributed computing, consensus protocol, transactional memories, etc. His research includes also other exciting topics, including like distributed machine learning and blockchain systems. So Rachid got his PhD from Paris, and after that he was affiliated with many research labs and institutions in Europe and the United States, including Hewlett-Packard and MIT, before joining POPL in Switzerland. So, okay, I will not take a lot of time for the introduction, more than what we spent already. So I will let him present us his talk here about this very intriguing and promising title. Before he will start, please, if you want to send, you want to ask questions, write them on the chat during the talk. Don't wait at the end to write them, so that at the end of the talk we can have, we can proceed directly to answering the questions. So please write your questions immediately when you have them on the chat. Okay, Rachid, please go ahead. Thank you very much, and hope everything will work this time.
Yeah, before you remove the mic, can you just tell me whether you can hear me?
Yes.
And you can see this?
Yes.
Okay, good. Thanks. Thank you, Ahmed. Thank you for the nice introduction. I am indeed at EPFL, École Polytechnique Fédérale de Lausanne. It's a nice place, and we are actually have people working on programming languages and always hiring good students and good faculty. This talk has this indeed intriguing title, as Ahmed said, In Search for Lost Universality, inspired by the famous book of Proust. And it's supposed to be somehow a call for the programming language folks to help fix some of the distributed computing problems. I did my studies a long time ago when I was doing my PhD. I used to go to ECOOP and UPSLA. And in those days, object-oriented programming was a hot topic. And when it became mainstream, many people from there moved to POPL, and I'm happy to meet or e-meet some of them today. I actually back then saw the light and moved to distributed computing. So this is a journey to the center of distributed computing. And of course, it's going to be very biased and very subjective. I will give my perspective of what this field is about and what it has been about for the last decades, and why I believe that programming language people can really help this field. Okay, so this is the roadmap. The talk will be divided into three unequal parts. The first part, which is what I call the lost universality. I'll try to explain, of course, what I mean by that. And roughly speaking, the idea is that once we moved to distributed computing, we lost the nice universality of Turing machine. And then I will try to explain that the last decades of distributed computing were mainly about trying to recover, to find that lost universality. So that's what I call the quest for universality. And then these days, what people in the field are doing is to build a new universal internet machine. Let's call it a distributed Turing machine. This is what we are doing these days. And that's where really programming language people can help. Okay, so let me go back in history to explain what I mean by, or recall what I mean by universality. Many of these things are trivial to you, but hopefully you will see the analogies with what would come later. In the old days, people used to write algorithms for other people. of course, those who were writing algorithms were very smart mathematicians, and they were writing algorithms for other less mathematician people to help them solve some problems. So Algorithmi wrote this sum algorithm by defining also the adequate data representation so that anybody could perform some computation. If you try it with the Roman numbers, it's much harder. So he had to invent the data representation to enable the average non-mathematician person to do that. But there was some form of universality because everyone could just read the book of Algorithmi or others, learn or try to digest the algorithms presented there, and then perform the algorithm, be it a sum or solving a second-degree equation or what have you. But then we realized indeed that the way people were writing, were executing these algorithms, they were behaving like machines. And then some smart mathematicians / inventors decided to speed up the process by, instead of having people execute the algorithm, have machines execute the algorithm. So Blaise Pascal built a machine where the algorithm of the sum was basically hard-coded. But the machine was much faster than people who were executing the sum algorithm. Unfortunately, we lost universality. There was one algorithm in that machine. Leibniz later, I think he built a machine to do multiplication, but it was only doing that. And as we all know, it took few centuries until Turing came with the bright idea to consider algorithms as data that you could inject in the machine, pretty much like Algorithmi was injecting in the mind of his followers the algorithms that they could learn, digest, and then execute. So we already lost universality by moving to the machines, and then Alan Turing came and fixed it somehow by considering algorithm as data of a machine. So the second time we lost universality, and this is people who work on distributed computing, of course, will know what I'm talking about, but maybe for the others, the way to consider these things is slightly different. There were two big moments. Both of them are related to trying to build better machines, so to speak. And there were two fronts. One of them is to try to speed up the computing capabilities of machines and have a lot of them in a very narrow space, a lot of Turing machines in a small narrow space, and try to have them communicate with shared memory and parallelize the code. This is what I call the infinitely small. People tried to build parallel computers, but while doing that, what they were doing is take a lot of Turing machines and put them in a very small space, have them communicate in shared memory. Almost in parallel, although slightly earlier, there was another front also putting Turing machines together, but now trying to geographically separate them in order to reduce or diminish the probability that machines would fail at the same time. So the motivation of the infinitely small was speed, and the original motivation, at least, of the infinitely big was high availability, because a single machine was fragile and slow. And what we tried to do was to make it faster and more reliable. The claim here is that by doing so, by trying to put these Turing machines together, people did not really realize that they were losing the nice feature of universality. They gained speed and availability, but they lost universality. And this is what I will recall or explain now. One observation. These two fronts, one of them building shared memory computers to parallelize computation, and the other one, which is to build large-scale systems, have been represented, captured by two models from theoreticians. They basically what we call the shared memory model or the message passing model. Usually, it is considered that in the shared memory model, the worst things that can happen is that some machines would go slower than others. In fact, we talk about processes or processors, and we give the name machine to the sum. Similarly, people considered that, and in the first part, in the shared memory world, it was typical to assume that the worst thing that can happen is that some processes would stop or get at least much slower than others. In the other front, where the goal was more reliability, it was typical to assume that processes or machines communicate by message passing, and there we assumed that worse things could happen. People could attack the system. So there were two kinds of fronts from the theoretical perspective representing what the engineers were building. So in the message passing world, the infinitely big people were considering, the theoreticians were representing things as processes exchanging messages. And an adversary which can slow down the messages, but also corrupt them. From the shared memory parts, people were rather considering processes reading and writing in memory, mimicking what was actually happening in the actual multi-core architecture. And here the assumption is that the memory is composed of units, registers, typically assumed to be atomic, but on which you can only read and write. So here you don't exchange messages, you read and write in registers. With an adversary that can slow down messages. Of course, the notion of adversary is simply an assumption that in your execution, certain things could happen. And here, the bad things that could happen is that some messages can take very long time. The time to write or read from atomic registers can take arbitrarily long. One of the most fundamental results in distributed computing is that these two models are equivalent. From a computational perspective, they are equivalent. They are equivalent modulo one assumptions on the bad guy or the adversary of the bad adversary on the message pass in front. If we have a large enough number of correct processes that the adversary cannot control, then we can emulate a shared memory. The emulation from shared memory to message passing does not require that assumption. But if we have an assumption of a large number of correct processes, typically called quorums, to make things simple, in a system of 100, 51 are correct. Of course, the notion of quorum sometimes is more sophisticated, but in this talk, let's stay with that. So these two models are equivalent, modulo some assumption on the number of correct processes in the large-scale system. So this is one of the most important results in distributed computing, and I will come back to it later. So what do I mean by losing universality in these two worlds? So the claim is that when we move to these two worlds, which are somehow, at least computationally speaking, equivalent, we lost universality. Again, remember, the motivation is to be fast and highly available. And I will try to explain that better. But the claim here is that when we try to do that, we lost the of universality. And to see that, let me focus on the shared memory world. Now that I told you that actually it's equivalent to the message passing one, let's focus on the shared memory world and ask ourselves whether we can indeed implement everything, whether we are universal. And let's assume, for the sake of simplicity, that what we want to implement is some very simple object, which is a counter. We want to implement an object that we can increment and read. And this object maintains integers initialized to 0. And the sequential specification of this object is that we can read it and it returns to us the state of that object, initially 0. And we can increment it. And when we are done with the incrementation, it returns OK. Okay, so we want to implement this object. Now, what does it mean that we want to implement it now that we have moved to the infinitely small world where we have a lot of processes? We want to implement in the sense that we would like any process in our shared memory architecture to be able to invoke the read and increment operations in such a way that they are correct. And correctness here typically means atomicity. Everything happens as if one process invokes an operation, takes the time to finish, and then give the hand to the other process, as if they were using a lock. But we also want these to be highly available, so we don't want them to use locks. So this is the meaning of implement. In the parlance of memory, we say we want them to be atomic and weight-free. So is there an algorithm to do that? Sorry, before showing you this slide, ask yourself, how would you do that on a shared in a shared memory system? So you have registers. You can say, maybe I can have one register to implement the counter, because this is what we have. We only have registers. And whenever a process wants to read, it reads the value of the register implementing the counter. And when you want to increment, you read the value of that register, you increment it and write it back, because you can only read and write. It is easy to see that this is not going to be atomic, because you can read and the adversary makes you sleep, and then somebody else comes and writes value 1, value 2, value 3, etc. And when you come back to write, because you were sleeping in your incrementation, you take everything back to 1. Okay, so you can lose a lot of updates. So this is not a correct algorithm. It is not atomic, but there is an algorithm, slightly more sophisticated, but not that much. What you do, if you have n processes, you use n registers, and when you want to increment, you indeed read the value of your register. So there are n processes. Every process has a register devoted to it. Only that process can write in that register. A process can read in all of them, but it can only write in the register devoted to it, reserved for it. So process P1 will read the register. This is what's in this code here. Then increment, then write back. And when we want to read, you basically read all registers and then sum them. By doing so, you prevent the problem I just pointed out, and you have a very nice counter, which you can prove to have the good properties, which is atomic and weight-free, highly available. Okay, so this object here, we can implement. We did not lose universality. We did not show that we do lose universality. But what if I go to this slightly improved object where I have, in addition, an operation called decrement. So here, in addition to read and increment, I also decrement a value. If the value is strictly superior to 0, then I can decrement it and return OK. Else I return no. Can I implement counter star under the same setting, in the same setting with shared memory and the adversary that can arbitrarily slow down processes? Now things become slightly more complicated, and in fact, people have been trying to do this a long time ago, not realizing that it was impossible. Of course, today it looks obvious that it's impossible, because people would say, oh, but these operations do not commute, or whatever terminology you use. But let's go back 30 years ago. People were really trying to implement this counter, until somebody came and then made the link with another fundamental result in distributed computing by showing that, in fact, this counter star can be used to implement an object that was actually known to be impossible from a completely different setting. So and this is a very simple proof that counter star cannot be implemented. You show it by showing that you can solve an object called consensus, an abstraction called consensus. And you can solve consensus among two processes using counter. So what is consensus? Consensus is an object that also has a specification that is as simple as the counter. It's even simpler. You have only one operation, which is propose. So the consensus object, unlike the counter, does not have read and increment. It has an operation propose. You propose a value. Processes can propose different values, and the propose operation returns the same value to all. And the value returned has to be one of the values proposed. So Ahmed, myself, Jens, Benjamin, Michael proposed that what movies are we going to see tonight? And then the consensus object gives us back one of the movies. Here is a simple algorithm to implement consensus among two processes, only Ahmed and myself, using this counter object. You use a counter object, and you use as well registers. You always assume that you have register. You use this counter star object initialized to 0. So how do you solve consensus? I propose my value. Let's say my value is 0. Ahmed proposes a value, which is 1, and we execute this code. So when I propose my value, I write first my value in my register, and I go to the counter star. I decrement it. And the result of the decrement is going to be, assuming that the counter star was initialized to 1, is going to be either either OK if I manage to decrement first, or it's going to be no if I did not manage to decrement first. If result is okay, I know I won. Somehow I was the first. In that case, I decide my value. If result is not okay, then what I do is I read the other register, the register of Ahmed, and there I will find the value. It's actually easy to see that using this fact that only one person, given that the register is the counter is initialized to 1, only one of us can get okay. It's easy to see that you break symmetry and you can decide on one value. So counter star, implement consensus. Good. And it turns out that when people were trying to implement these abstractions, there was an interesting fundamental result in distributed computing showing that no asynchronous algorithms implement consensus among two processes using registers. Okay? So in fact, the original result was for message passing, Fisher, Lynch, and Patterson. Though in those days, we didn't know that the two models were equivalent. There was some intuition, but it was not clear. So there's another proof that shows this actual theorem by Louis and Abu Amara in '87, showing that indeed no asynchronous algorithm implements consensus among two processes using registers. As a corollary, no asynchronous algorithm implements counter star among two processes using registers. Remember, what I call asynchronous here, what I mean by asynchronous is the presence of this adversary, which can delay for arbitrarily long the time it takes for a process to read or write in a register. At this point, you might ask yourself whether this assumption of asynchrony is reasonable or not, and I will come back to that later. In fact, one of the most beautiful results in distributed computing is a generalization of this. So here, the result is several processes cannot agree on one value. If there are n, they cannot agree on one. In fact, the results can be generalized and to the point of showing that you cannot even remove one value. Even you ask the n processes, you tell them, okay, you can disagree, but I want you to decide on less than n values. So I can decide a value, Ahmed can decide a different value, Michael another one, etc. As long as the number of values at the end is n minus 1. We somehow remove the value. And it turns out that this is also impossible. And this can be shown by a reduction to Sperner's lemma. And it was done by different teams in, I don't remember the year, but this is a very interesting result in the field. I apologize for the authors. I only remember some of them, and that's why I don't want to be unfair and just mention some and not others. 3 teams have demonstrated this. Okay, good. So what I have tried to say here is that this notion of universality was lost when we tried to go from one machine to several machines. And it was lost on both fronts, on the infinitely small and multiprocessor, as well as on the message passing side. And the way to prove that it was lost is because many abstractions that we really wanted to implement, the counter is an obvious abstraction, but many others, like a queue, like others, actually are as strong as consensus. You can use them to build consensus, which was shown to be impossible. It was shown to be impossible in the general case where we don't make any assumption on that famous adversary, meaning we assume that the adversary is very strong. So those were the main results 20 or 25 years ago. And then what people have been trying to do in distributed computing, at least some fraction of people, was to recover back that universality, the quest for universality. So here, there were some other results that I will sketch, which were actually very interesting and important. The first one was actually an old result by Lamport in '78, showing that consensus is actually sufficient. Of course, what I have just told you is that for many objects, consensus was necessary. What Lamport has shown is that consensus was also sufficient, meaning if you could implement consensus using what Lamport called at that time, when others called at that time state machine replication, you can implement any abstraction, any object. Basically, what Lamport has shown is that if you can have a way to make the Turing machines solve consensus, then either at the infinitely small or at infinitely big scale, you can implement everything. But as I just pointed out, consensus is impossible. Yes, it's impossible in the general case, in the general sense. And hence, the quest was to try to limit the scope or try to boost the architecture or make specific assumptions such that we could solve consensus. Because we knew that if we could solve it, we could do everything. So consensus is necessary, but also sufficient. So what were the main tracks to circumvent the impossibility of consensus? From the hardware level, there was a very, very interesting line of research, basically saying if you take an architecture which has read-write memory, and in addition to the registers, you add objects, synchronization objects that are more powerful, then the impossibility of consensus doesn't hold anymore, and you can solve it, and therefore you can be universal again. For example, if I have a test and set object in my architecture, I can solve consensus among two processes, which means in a system of two processes, I am universal. If I have a compare and swap, I can solve consensus among any number of processes, which means that I'm universal for a large number of processes. Maurice Herlihy defined the analog of Mendeleev's table for a hardware synchronization object, defining not the atomic number of an element, but the consensus number of an object, the maximum number of processes that can solve consensus with it. So now, if I am Intel, I come to Maurice Herlihy and ask him what object should I put in my architecture in order to be universal for n processes, for any number. Maurice would say compare and swap. But maybe compare and swap is too expensive. Maybe I need only this object. It was shown that you can define an object that has exactly any number you want. So you have a hierarchy from that perspective. So this is one line of research, okay? Building universality by boosting the hardware. Another line of research, which was more a line of research in the front of message passing, because this is not something you could do in the message passing world. You could not really boost a network. What are you going to do? Building a compare and swap in a network is difficult. So from the message passing perspective, what people have tried to do is to make some assumptions about time, reducing the scope, reducing the power of the adversary. Instead of saying the adversary can do anything, maybe we can assume a synchronous system where the adversary cannot arbitrarily delay messages. That was one direction. Another direction, which I personally found very elegant, was to say, why don't we build our algorithms in such a way that as long as the adversary is nasty and it is really delaying messages, we are not violating atomicity. We don't violate safety. But if we have a window where the adversary behaves, so to speak, and enables us to exchange messages in a bounded manner, then we will reach a decision, solve consensus, and whatever. And this is the line of algorithms like Paxos or PBFT or Chandra and Twig and others. I call them indulgent algorithms because they forgive the adversary's nastiness. There have been a lot of work in this direction, how to build algorithms that have this property, what we called with colleagues from EPFL speculative linearizability or other colleagues, a way to build these kinds of indulgent algorithms. I will skip the weakest failure detector question, but this is something very elegant that has been followed to define exactly what is the power of the adversary, the maximum power of the adversary, such that you can solve consensus. It is important to notice that in the last 2 decades, there were the work on shared memory, the work on message passing, but then more recently, there is something that just came up, which basically changed a little bit the game. RDMA is that. So what is RDMA? For those of you who know it, forgive me. For the others, think of it as mixing shared memory and message passing. It's as if you can, processes, even if they are geographically distant, they can read directly in the memory of the other. And you could actually define this model and show that it's strictly stronger than the message passing model. It's a very interesting model. So there have been a bunch of results in this world. And you could, for example, whereas in message passing, to solve consensus, you need 3f+1 if you have a nasty adversary that can corrupt messages. You can show here that you only need 2f+1. So somehow this model is an intermediate between message passing and shared memory. With colleague from EPFL, we even built some kind of a universal machine on this kind of architecture. Now, something that is very important to highlight. Even if you circumvent the impossibility of consensus, either by boosting your hardware or by making some timing assumptions, you can indeed show that you can solve consensus. You realize that actually you have just turned the impossibility of consensus into some delays, some latency, hampering your performance. So this is something to keep in mind. So even if we succeeded into defining the subset of the world where we can solve all our problems, in fact, what we did was turning impossibility into complexity overhead. We have a paper on that one with Eli Gaffney at Stock for those of you interested in this relation. Let me skip this. Okay, so consensus is sufficient, and people have tried to consider a less general model than the asynchronous one and build a universal machine. Let's call it a universal internet machine, because we still we can work over the internet. But as I just pointed out, even if we could circumvent this impossibility of consensus, we just paid another price, which is paying a lot of overhead and hampering complexity. So another research direction was the following, and I will try to explain it. This will be the third part of this talk. How to use this universal internet machine that we could build. So we have a machine, either a shared memory machine with comparand swap or whatever, or a large-scale message passing machine where we make some assumptions about the adversary and we build algorithms that are indulgent at this and that. The point here is to how to use this. And this is very important. It is not because you have this big weapon, which is consensus, that you have to use it all the time. In fact, here comes an interesting research direction, which is what are the objects that really need consensus and those that do not need consensus. If you don't need it, don't use it. And I'm going to give two examples, the Bitcoin or the payment problem, as well as a machine learning example. And these will be two examples that, in both cases, people believed that you would really need consensus to solve them, just like counter star. In fact, it turns out that they resemble more the counter, even if they look much more complicated. Okay, quickly. The Bitcoin problem, as I call it, is actually well defined in the original paper of Nakamoto called the double spending problem. So you can define the problem solved by the Bitcoin protocol or the thousands of implementations of Bitcoin-like abstractions, virtual currencies, and they all basically solve the same problem. It turns out that most of them, if not all of them, solve consensus because the original algorithm of Nakamoto was solving the Sybil attack problem with the leader election mechanism that also solves consensus. So he was circumventing the impossibility of consensus because he assumed something about time, but the algorithm is very expensive. It turns out, I'm going to skip this, if we ask the question, do we need consensus? Another way to ask the question is the problem asynchronous? Can we solve it in the asynchronous world? In fact, it turns out that if we remove all the noise around the virtual currency definition and simply define the problem in a very succinct manner, you can actually realize that it's actually very easy. What is this object that I call here the payment object, as defined in Nakamoto's paper? It has an operation, pay A, B, X, basically saying transfer amount X from A to B if A is bigger than X, amount A is bigger than X. And in the double spending problem, as defined by Nakamoto, only the owner of A invokes pay A, BX. So I am the owner of A, I can send some money to Michael to thank him for helping me share my slides, and only I can do that operation because it's my account. I'm not going to go into the details here. We have a couple of papers that define that show that, but you have to believe me, it's not very difficult. You can show that you can use an object that is widely known to be asynchronous to not need consensus, called the snapshot object. So a snapshot object is an object that you can update a value and scan what everybody has updated. It's just like everybody posting something on Facebook. This is update. I update my wall. And then from time to time, somebody named Mark can scan the entire system and see what's going on. This object, even if it looks impressively hard, it's not hard. It's not hard in the distributed computing sense. It is asynchronous. We can implement it just like we could implement counter. If you can implement this object, trust me, it's not very hard. You can implement the payment object. I'm not going to give you the algorithm, but it's actually very easy. Just think of Facebook where everybody...
Looks good.
Okay,
yeah,
sorry guys. Okay, good. Good. So the reason why we lost universality is because consensus was shown to be necessary for many of those problems, but unfortunately impossible. And this is probably the most important result in the field. But then it was also shown by, which is probably the second or the first, depending to whom you talk, most important result in the field, was that if you can solve consensus, you can solve every object, and you can therefore regain or recover the universality. But of course, consensus is impossible, and therefore the game and the research that people were doing in this field was defining the assumptions under which consensus is actually possible. I call it sometimes possible. So one line of research was the boosting the hardware of shared memory machines and multiprocessors. And I believe this is something I already explained. If this was cut after the problem, please read the fantastic papers of Norlis Herlihy on the notion of consensus number. There was another front which was about time, reducing the power of the adversary by basically assuming that it cannot delay arbitrarily long messages. It cannot delay messages for arbitrarily long, but sometimes the adversary behave. So here, the extreme is to assume that the system is completely synchronous, the adversary is weak, but the middle ground was to assume that maybe the adversary is not nice, but sometimes messages arrive in time. And this is the notion of eventual synchrony that people have been working on. And there was a flurry of papers in this area. You probably heard about Paxos, PBFT, Chandran 2x algorithm. There have been even ways to generate these kinds of algorithms. And here I'm mentioning a couple of works with my colleagues, Victor Kunchak and Giuliano Loza, as well as Marko Vikolic, on how to generate such algorithms. I don't want to spend time talking about the weakest failure detector question, but again, this is something very elegant and nice. Technology also has been changing, which changed a little bit the game. We don't have only this pure shared memory, pure message passing model, but the RDMA model somehow came as an intermediate where we could do things and somehow gain the benefits of shared memory, at least some of the benefits of shared memory in message passing. And this new model also has been explored, and we have been asking ourselves, how do we build consensus in this model? So we built a system called the Mu, and we published recently, which solves consensus in 1 millisecond, but in 1 millisecond in the best case. Okay, good. So we lost universality when we weren't distributed. We spent 2 decades of work defining exactly when we can circumvent the impossibility of consensus and build a universal machine. But while doing so, we also realized something, that even under the circumstances where consensus is possible, we basically pay some price. And you could actually prove that impossibility results on consensus in certain situations like asynchrony. You can transform those proofs into lower bounds on consensus in a synchronous system. What I'm saying here is that even if you put yourself under the conditions that you can solve consensus, you realize that it is expensive. So to just give you a simple idea, in a shared memory system, if you go and use compare and swap is expensive. That's easy. But you can also show that if you go to eventual synchronous system where you can solve consensus, it's actually, you pay the price in terms of complexity. So now the challenge has also been, when can we actually circumvent the usage of consensus? Of course, we have a machine where we can do consensus. We know that certain objects, to certain problems, to solve them, we need to solve consensus. So it's important to have algorithms that do consensus, but it's also very important to try to see and remove consensus whenever it is not necessary. And it turns out that in some cases where it looks very necessary, actually it is not. And the two examples I picked for this talk was the Bitcoin problem, or the double payment problem, and the machine learning problem. So is Bitcoin an asynchronous problem? What about learning? So what I call an asynchronous problem is a problem that does not need consensus. So the world of classical computing is divided, roughly speaking, into P and NP, what is easy and what is hard. Now the world is divided into which problem is asynchronous, easy, which problem is hard. Is Bitcoin an easy problem or not? Of course, if you look at the original paper of Nakamoto, and if you look at the 1,000 implementation today, most of them, I think all of them, most of them, let's say, actually make use of consensus. They first build consensus and then they build the payment system. In fact, if you look carefully at the paper of Nakamoto, which I'm sure many of you have done, Nakamoto defines the problem of double payment, and to solve it, uses a mechanism to elect a leader that serves two purposes. One of them is to fight Sybil attacks, and the other one is to actually solve consensus. And since many people followed the track of Nakamoto and the Bitcoin protocol, they were solving consensus. In fact, you can show that you don't need that. And remember that I told you that message passing and shared memory are computationally speaking equivalent. So we studied the Bitcoin problem in the shared memory model, and then we translated our results in the message passing model. And the question here, if you ask it with the lenses of the theory of distributed computing, is given an object where a process can transfer an amount of money or some amount to another process under the condition that I have enough money to transfer money and I have enough money to do the transfer, is this object something that we can implement in a weight-free atomic manner without needing consensus? Or, in other words, what is the consensus number of this object? I claim that this very simple specification that I'm giving here is exactly the double payment problem defined by Nakamoto. Implementing this object in a weight-free atomic manner is exactly solving the double payment problem of Nakamoto. Of course, the assumption is that only the owner of A can invoke this operation on the object. So if I want to thank Michael for his help and send him some money, then I will use this operation. But Ahmed cannot do that on my account. So this is very important. So here the question was, can this object be implemented asynchronously? What is its consensus number? You have to believe me here that in fact you can show that if you have an object, that you can use an object that is known to be asynchronous in the distributed computing world, which is the snapshot object, you can implement this one. So what is the snapshot object? Snapshot object is an object that on which you can invoke two operations. One of them is update IV, and I is the identity of the process invoking the object. So if we are n, each of us can invoke update 1, 2, 3, and this basically somehow captures a place in the memory. Think of Facebook. I have an account, I post on my wall. Michael goes, posts on his wall. Benjamin does the same, Jens does the same. So we say, I'm happy, I'm not happy, the weather is great, etc. And then let's say Mark can scan the system and it can see immediately in an instantaneous manner what's going on Facebook. And this happens atomically. This is the snapshot object. And even if it looks impressive and amazingly powerful, you can show that this object can be implemented asynchronously. And this is, I think, a very beautiful algorithm by Atia, Gafni. I keep forgetting my friends in Israel, and I apologize. But a bunch of smart Israelis have implemented this algorithm. It turns out that if you solve this problem, you can implement the payment object. Given that this is asynchronous, this means that the payment object is asynchronous. Its consensus number is 1, meaning it's a very, very, very easy problem. Yes, implementing Bitcoin is very easy with respect to distributed computing metric. Moreover, you can show that if you can, if not only I can access my account, but Ahmed can access my account and Michael, and we are 4 people that can access my account, which is not the original problem of Nakamoto, which is another object that we can call a smart contract shared by 4, then the consensus number is 4. Okay, so this is a very interesting result because it somehow tells us if you want to do business with K people, then the consensus number is K, which is in retrospect is not very surprising. But if you look at the 100 of papers on smart contracts and Bitcoin, they all use consensus, as if the consensus number was infinity. So starting from this theoretical result, showing that the consensus number is 1, you can actually go back to the message passing world and implement algorithms that I argue to be much easier to understand and much faster than the original Bitcoin protocol, let alone talking about energy and so forth. The second example, and this is the last one, is the machine learning problem. Of course, people have been implementing distributed machine learning algorithms because the amount of data is huge, so they had to use different machines. And the classical setting is one parameter server owning the model, and then a bunch of workers doing some gradient descent, and this parameter server in the classical scheme doing some averaging. Of course, if you have a malicious player, averaging is a disaster, because if everybody's saying the temperature is 15, 16, 17, and one guy says the temperature is 2 million, then of course your learning is going to be slightly screwed. So the idea here is to do a better gathering of information and use other mathematical function than averaging, like median and things like that. So this problem of building a distributed machine scheme that can tolerate some bad players, let's call it the distributed learning problem. And we can ask, is this problem, even if the simple form where we have one parameter server, is this problem, does it need consensus? And if you look at it and read some of the original papers, you might believe that yes, it does. In fact, it does not. You can actually show that this is also an asynchronous problem. It is also asynchronous even if you try to have several parameter servers, or we have a bunch of players trying to learn together. And we have been writing some algorithms in this world showing that you don't need consensus, but also building algorithms that we believe are quite effective. The machine learning community seems to have liked this line of research, and now there are tracks in NeurIPS and ICML on Byzantine machine learning and things like that. Again, this is an easy problem. Okay, last slide. Where do you guys, how can you help programming language people? How can you help this quest for universality? Of course, the universality came from the Turing machines and to some extent from programming languages. But now universality has switched. We have this internet universality. I see at least 2 places that are extremely challenging where the skills of the POPL, PLDI, ECO, POPSLA communities could be of great help. One of them has already started being used. I see the papers at POPL and PLDI with how to write the algorithms of this universal machine, how to write the consensus algorithm that is indulgent and has this and that property, how to write the causal broadcast algorithm, which is weaker than consensus and which is enough for Bitcoin, how to write the machine learning algorithm. In my experience, and to be honest with you, in the experience of my PhD students who do the actual work, it's a nightmare. It's a nightmare as long as you want to prove things and to preserve whatever property you have shown on the C or the language. And this is something difficult. And I know that the programming language people can really help a lot. I share my floor with Victor Kunchak and Martin Odersky, and their help has been to some extent very helpful, and I think more help would be great. But there is another line of research, which is the last thing I'm going to mention, which is how to write the actual program on that machine. So assume you want to write the counter or the counter star or the Bitcoin or whatever. Wouldn't it be great if the compiler or some tools somehow guide you in such a way that you don't have a higher consensus number than you need? If you want to write a counter star, maybe the tool will tell you, do you really need the decrement operation? I'm taking something very simplistic here as an example, but a compiler who will tell you, oh, in this Bitcoin protocol, do you really need to share this account with K people? Because if you do that, that means the underlying algorithm is going to be much more expensive than if only Rachid can do that. I'm taking here the two examples that are very trivial, almost trivial. It's like saying, why do you need non-commutativity or something like that? But I really believe some compiler skills will be amazing here. Okay, I hope that you could hear me until the end. I see some people connected, so I believe it's all fine. Okay, good. Okay, so thank you very much, Rachid, for this great talk. And sorry for all these interruptions and this disturbance. So let's proceed to some questions. I see two questions already on the chat. I mean, both of them are about this objects. Okay, so I mean, the first, let me read the first one. What is the object? Can you read the chat yourself, or maybe I can just read them for you? What is the object? Please
read it aloud. Yeah, make sure it's aloud so it's in the recording.
Sorry?
I'm sorry
okay,
to interrupt.
sorry. Yes, sure. What is the object being snapshotted across the network in this model? I think it's about the model you showed for the snapshot, object. Okay, so the full state of each node. So this is the question: is it the full state of each node, an account, the head of the chain? Does it matter?
Yeah, okay, so you have to realize here that the way at least we do these things is, first we go to the shared memory and we say, in this shared memory, let's implement this, let's see whether we can implement the payment object. Oh, we know we have the snapshot object that we know we can implement. Let's go brute force and implement the payment object. We don't care here about the distributed setting in the message passing sense. It's just about implementing this payment object. And in fact, we could implement it. Oh, good news. This means this object is easy. We don't need to agree. We don't need timing assumptions, etc. Good. Now, we can use the classical equivalence results between shared memory and message passing to translate our algorithm, including the snapshot object, to the message passing. But that's a very, very bad idea. We just know it's possible. So now our implementation is actually completely different from that. You don't need the full state of every object. I cannot really tell you the full algorithm here, but the disk paper that I mentioned actually shows how to do that in a rather effective manner. Roughly speaking, if I want to send money to Ahmed, and Ahmed doesn't trust me because he doesn't know whether I'm not trying to send the same money to Michael, then what Ahmed would say is basically ask around, did anybody see Rachid sending his money to somebody else? And he will sample around him. And Michael will also do the same. And we can show that if the samples are big enough and uniformly distributed, the chances that I succeed in double spending are very low. This is roughly speaking the idea. It has nothing to do with implementing snapshot, much easier. But you can sense the idea of having a global picture. So this was my answer to the first question.
All right, very good. So actually there is another one which is somehow related. It's about also this alternative asynchronous Bitcoin implementation. Does it still have the same cryptographic trust assumptions? No central authority, mutual distrusting peers, and so on.
Yes. The answer is yes.
Okay. Right. By the way, the first one was the question was asked by German Andres Del Bianco, and the second one by Ralph Young. I'm just citing the names so that. And there is another one by Philip Wadler. Thank you for the great talk. In practice, against the sort of adversaries that arise in the real world, how practical is your efficient solution to the easy Bitcoin problem? Are there any startups yet?
Yes, thanks, Michael. I remember giving a talk at AT&T a long time ago, and the nasty question was from you. So thanks for asking again question. This one is not a nasty question. The two elements of comparison that we had was, one of them is the number of lines of code. It turns out that when you move consensus and you use a completely asynchronous algorithm, it's one order of magnitude that you gain, which is not something to be neglected when you write distributed algorithm. The second metric had to do with how basically the worst case. In the best case, when there is no contention, the system is synchronous, consensus is very fast. And even if you have an abstraction that is weaker, usually it doesn't beat consensus on that fast path. However, when something bad happens, for example, when you have elected a leader in the consensus algorithm and the leader starts doing the transaction ordering, and then that leader fails or gets slowed down, now things become complicated with consensus algorithm. You need a new leader, you need this and that. And in that subset of executions, you can show that the algorithm that we have used, which is some kind of causal broadcast, is much more efficient. And please, you can read the DSN paper, and I would be happy to share it even more with people who are interested. But there is a significant gain on both metrics.
Okay, another question by Ilya Sergey. So thank you for a very nice talk. Question: in my understanding of how consensus protocols are used, transitions of replicated state machines are considered opaque. The consensus protocol is not supposed to know what they do internally besides updating the replicated state. Do you think it would make sense to expose some application-specific intrinsics, e.g. memory footprint, to the protocol for, e.g. reaching a consensus faster?
Yeah, I think this is a great suggestion. It was done to some extent by Fernando Pedone, André Schipper, Leslie Lamport, by somehow I think the algorithms were called generalized Paxos or adaptive Paxos or something like that, where you could indeed derive something from the application and use it in the consensus algorithm, roughly speaking, to say these two messages do not need to be ordered, these messages need to be ordered. My suggestion at the end of my talk was really to say, can we generalize that not only to applications for which we know we need consensus, but for general purpose programs, and say, okay, well, in 99% of this program, there is no need for consensus, let's do it, or maybe reduce the program in such a way that it doesn't use consensus at all, etc. So my suggestion was along these lines. Yes, thanks.
So since there are no other questions on the chat, maybe I just want to follow up on this question in the sense, I mean, this is somehow in my understanding related to the question of how to choose the right level of consistency between, let's say, a system and an application also, right? Because for instance, when you say that's, okay, I mean, a question is when you are talking about universality, as you said, you are talking about the criterion of correctness, which is related to atomicity. Now, if you don't need, in fact, this atomicity, so you may relax in some sense the correctness criterion, then of course you can only implement maybe weaker objects. But how this is related, you know, to all this issues of consistency like causal consistency, snapshot isolation, and all these questions that are, investigated in, let's say, distributed databases and other, similar contexts.
Yeah. Good question that I did not address that today. My claim today was, let's assume we want to build programs that look like as if they were executed on a Turing machine, which essentially says atomic. So the entire talk was, let's assume this is what we want. If this is what we want, there is still can be hope, because many of the objects, even if they're not atomic or want them to be atomic, are not that hard to implement. So this was the claim. Of course, if we don't want them to be atomic anymore, then most probably they will be much easier, but it's not clear what we are doing. And we can have another discussion on that, but I think it's a good question.
Yeah, for instance, if let's say that you take as your reference is snapshot isolation or whatever, I'm just taking an example. Maybe then you can say that you can reach some level of universality, which is depending on this level of consistency that you have taken.
Yes.
I mean,
yeah.
Somehow universality, the notion of universality is relative to something.
Yes, I completely agree with you. And maybe we can show that if you start from snapshot isolation, then you reach this level of consensus number -5 or -4 or whatever. I don't know.
Okay. So thank you. So any other questions or comments?
Excellent.
Look, that and there are no other questions. So thank you very much again, Rachid, for this great talk and for this nice discussion. And thanks
you, Michael.
everybody for the participation.
Thank you, Michael, for your help. Thank you, Ahmed.